this afternoon we will have another topic under the chapter of gas power cycle, thermodynamics in heat transfer. For a part 2 problem, an ideal diesel cycle with air as the working fluid has a compression ratio of 18 and a cutoff ratio of 2. At the beginning of the compression process, the working fluid is at 14.7 pSi, 80 degree Fahrenheit, and 117 cubic inch. Utilizing the cold air standard assumptions, determine the temperature and pressure of air at the end of each process, the network output, and the mean effective pressure. For our first part, let us find the temperature and pressure of air at the end of each process. So here, we have the specific volume for state 2, temperature and pressure of the air at the end of each process. So we are tasked to find for the temperature and the pressure of that air at the end of every process. So this is our second state, the specific volume of our second state. So this is the formula, the specific volume of air all over the R, which is the cutoff the compression ratio. So plugging in, this is the specific volume a while ago, it is given, and we have a specific volume at state 2 to be 6.5 cubic inch. For our state 3, we have this formula. It is equivalent to the compression ratio multiplied to our specific volume at state 2. So we have now our specific volume at state 4 to be at state 3 to be 13 cubic inch, and the same thing, same formula, just plug in the specific volume of the state 3 into this formula, but instead of state 3 we have state 4. So plugging in that and calculating, we have the specific volume for our state 4 to be 117 cubic inch. So this is the specific volume at the end of the process at state 4. Let's proceed to process 1 to 2. Since this is an isentropic compression of ideal gas, there is a constant specific heat. So with this, we were gonna use constant specific heats. We have here the cutoff ratio to be 1.4. I mean the compression ratio 1.4. We are going to find the temperature at the end of each process. So the temperature at our state 2 is equivalent to our initial temperature to be 540 Kelvin multiplied to V1 over V2, that is 18, that is the compression ratio, raised to 1.4 minus 1. So our temperature on our state 2 is 1716 Rankine. For the process on state 2, we have this formula. So plug in everything, and we have the pressure at state 2 to be 841 pSi. Moving on to process 2 to 3, we determine the volumes at the end of each process and from the definitions of the compression ratio and the cutoff ratio. So yes, we have solved this a while ago, the temperature on our state 2, and using this combined ideal gas law, assuming that state 2 and 3 of the pressure is equivalent to 841 pSi, we have a temperature of 3432 Rankine on our state 3. Processes 3 to 4, this is isentropic expansion of an ideal gas. So finding for our temperature at state 4, plugging in all the needed values, we have the temperature in state 4 to be 1425 Rankine. And same thing on our pressure, using this same formula. We now have the pressure at state 4 to be 38.8 Bisham. Moving on, let us find for the mass of the air. The mass of the air as the working fluid in our diesel cycle. So this is from the ideal gas law formula. So finding for our mass, it is equivalent to the pressure multiplied to the volume all over the universal gas constant and the temperature at 2. We have now our mass of air to be 0.00498 pound mass. For this time, we need to find, or we need to know what is or how much is the heat addition in this process. So heat addition using this formula, M at constant pressures multiplied to the differences between the temperature at state 2 and 3. So we have this mass, our constant pressure, and the differences between our temperature at state 2 and 3. Now the heat addition in this process or this cycle is 2.051 BTU. For our heat rejected, how much is the heat rejected in this cycle? So heat rejected into ang mass, then the constant volume, and the differences between the temperature at state 1 and 4. We now have the heat rejection, the 0.754 BTU. And for the network output of our cycle, under the cold air standard assumptions, we have this formula. So the network of the cycle is equivalent to the differences of the heat rejection and the heat addition. So plugging in, we now have the network output of our cycle to be 1.297 BTU. And last, for our mean effective pressure, using this formula, work net all over the specific volumes of at state 1 and state 2. We calculate that and we get the 110 PSI for our mean effective pressure. So in utilizing under cold air standard assumptions, we determine the volumes and the temperature at the end of each process, and from this definition of the compression ratio and the cutoff ratio. So this is all for our part 2 problem on gas and power cycle under thermodynamics and heat transfer. Thank you so much for listening, everyone, and see you in our upcoming videos.